right, go and turn your practice exercise booklets to practice exercise 109. Exercise 109. Now on this exercise, there is one problem that you would ordinarily use a calculator for, but I'm not allowing you to use one. You're going to have to figure it out using some logical deductive reasoning. So exercise 109, no calculators, you may begin. So we're surprisingly short of assignment, but some good thorough answers. I appreciate that, sir. All right, lesson 76. I'll let you scroll down. I'm lazy. Lesson 76. Bless you. going to put your pencils down, and we're away at this point. If you would, go and take out a pen and exchange so that you do not have your own. Pencils away, take out a pen and exchange so that you do not have your own. You would sign your name as the grader next to where it says exercise 110. Sign your name as the grader next to where it says exercise 110. There at the bottom of exercise 109. All right, let's go and take a look at the answers. These are 8 points each. 8 points each. Going across the top row, the answers should be 10, 6, 4, -1. Positive 10, positive 6, positive 4, and -1. Going across the next row, the answers should be -12, positive 360, positive 4, and 0. -12, 360, positive 4, and 0.
If they have the right number but they don't have the right sign, is that completely wrong?
Well, they don't have to have a positive sign. They could leave it signless.
It's supposed to be negative.
If it's supposed to be negative, they don't have the negative, it is wrong.
Completely?
Yes. Yeah. All right, and on the bottom row, 25, 8, I'm going to skip that next one for now, and 512 at the end. That other one is a bonus, so if they missed one, but they got the square root of 7,225, we'll count that in place of a missed question. Here's how to think through this problem. Because again, normally you would use your calculator. Now you could, I suppose, factor it up, but there's a much easier way. What is 30 squared, class?
900.
900. What's 40 squared?
1600.
1600, right? So 50 squared would be
2500.
2500. Notice we're getting closer. 60 squared, 3600. 70 squared, 4900. 80 squared. Do you see that at 80 squared, we're getting really close to this value? What about 90 squared? 8100. Whoa, that's too far. That's too big. That means my answer is somewhere between 80 and 90. But folks, the number ends in 5. There's only one way in math you can ever multiply two things and get a 5.
85.
5 and 5. It's gotta be 85. So if they figured out 85, count that in place of a missed question, but we don't take points off for getting it wrong. So 8 points each, plus 8 for the bonus, though they can't go over a 100. Question?
So if they got that one wrong,
It doesn't count against them, no.
I had 5 times square root of 285 for mine.
Ooh, okay, a little off on the division there. All right, questions? All right, should have been 289, not 285. If you were factoring 25 and 289, which is 5 and 17. So, all right, return to the owners if you would, please, once you got the score on there. And Quentin was first. Quentin, did you get 100? All right, great job. Any other hundreds, though maybe not as fast as Quentin? All right, several, all right. Any questions on any of these? Questions on any of these problems? Again, this is some basic algebra, but are there questions on any of these? Say, how do you get that answer? Going once? Going twice? Gone. All right, pass those in if you would, please, and I'll collect them from you. Pass those forward if you would, please, and take your homework out. You were practicing construction 21 for homework last evening, where you were transforming a triangle into a square. And we used the word transform once before in talking about proportions. And we said with a proportion, when you transform it, you don't change the essence of what it is, you don't change the fact that it's a proportion, but you change the way it looks. With a construction transformation, we are taking a figure that looks one way. We're keeping all the same square units, all the same area, but we're morphing it into another shape. And that's what we did in the homework last night. We took a triangle, we took all the substance inside, and we fit it inside of a square now, transformed a triangle into a square. If you would, go ahead and have your, if you did it on the back side of your notebook page, then go ahead and have that out as well. So we just need to finish the square for the notebook's sake, but looks like you did it there in the homework. Good, so there's the notebook and there's your construction there. Good, and the practice on the back. Whoops.
I did mine wrong. I did mine wrong. I tried to follow my other one, but I couldn't understand it, so I tried my best.
Well, it doesn't look like you did. When did you do this?
I did this morning before I came into school.
That's the problem.
I did it like way before. I didn't, well, not while I was
Because if you didn't understand it, what did I say at the end of the lesson yesterday? If you feel it all lost, go back and rewatch the video so that you know what to do. You may want to rewatch the video while you do your homework. That doesn't look like a particularly great effort. Now go and talk to me after class. All right, let's go and take a look at this here. And on your papers, you should have had a triangle. Didn't have to be anything special. I suppose could have been isosceles or whatever, but just some random triangle. And we actually started the construction by thinking algebraically, if you will. We thought in terms of area formulas. We have class A, triangle. And the formula for the area of a triangle is 1/2 BH. So the substance inside this triangle can be shown algebraically by multiplying the base times the height and taking half of that. But we want to transform this into what figure?
Square.
A square. Well, what's the formula for the area of a square? Sine squared. So we somehow want to take a half base height and morph it into sine squared. And I said what we want to do then is to use a proportion. We did a lot with constructing proportions in the last unit. Let's use that to our benefit. And I said, what proportion are we shooting for here, Ethan?
Mean proportional.
A mean proportional, so our proportion would look like what?
1/2 P over S equal is to S is to H.
A half B is to S as S is to H. Or you could say half B over S equals S over H and chicken out of the dowry. But I appreciate that you tried to sound very mathematically intelligent there. All right, so here's the deal. As I look at my figure, I don't know S. Agreed? That's really, I mean, if I knew S, any perpendicular would work. Side, 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 we get our square. So I just need to know how long S is. Well, that means I better know how long half of B is and how long H is. But I don't. So what are we going to have to do first? Genesis?
Construct the altitude.
Good. Let's start with H. I don't know H. I don't even see H. Let's put an H in there. So construct the altitude. Remember, this is construction 5, construction of a perpendicular. You open your compass a little past the line, make the arc. I'm going to shorten the compass a little bit. Make another arc here, go to the other intersection, make another arc. And then when we connect the dots, we will now have the altitude that we needed for the construction. And although I can kind of visualize half B, I don't want to guess half B, Chris. How would I get for sure half of B?
Count back at my thing. Would you perpendicular bisect it?
Perpendicular bisector, right. To bisect, and the only way we know to bisect is a perpendicular bisector. So go to an end of the base and open the compass up more than half, make an arc, go to the other end, arc below and above, because otherwise I'll run into my arm. And we connect the dots. And we don't want to get this line confused with the altitude. This is certainly not the altitude, but it does show me where half the base is. So I needed to know half base. That's right there. And altitude. Obviously, right here. Those are the two things I needed to make the proportion happen. So now we're ready to construct S class, which, as Ethan already said, is my mean proportional, which means we need to construct a mean proportional, which means if you forgot how to construct a mean proportional, you go back and look at construction 19. And so construction 19 says to construct a mean proportional, Jamie, we start by drawing a
Big long line.
big long line. And what do we do with the big long line, Jamie? I'm not going to let you out that easy.
You measure off half the base onto the line,
All right, there's half the base.
and then from that point you measure the altitude.
All right, so we measure the altitude. And we mark that off in succession. So again, you take the two extremes and mark them off in succession. You could, as an option, scribble off any excess. You could, as an option, label your half base and altitude as well. Now what, Quentin?
Then you would
Well, I already did that. I copied my half base, I copied my altitude.
You would.
And we took a quiz on this already once before. Audrey, helping? Not the perpendicular, bisector, the perpendicular. Remember this picture, Quentin? This is what we're shooting for. This is my half base, that's one segment. Altitude is the other segment of the hypotenuse. So that this will be the mean proportional. Segment will be to altitude as altitude will be to segment. So I'm trying to construct this, which means right here, I need to put a perpendicular that will be the altitude eventually. So that's what we're shooting for here. So come over here, make a little mark, make a little mark. Open it wider, make a little mark, make a little mark. And when we connect the dots here, we have the altitude of the right triangle. Now we don't have a right triangle yet, but we do have the altitude of it whenever we get it. And we're ready to go. And of course, that's where the mean proportional will be. Coming back to Quentin, does that kind of ring a bell on what to do next?
You need to find the midpoint.
Why do we need the midpoint?
To construct the semicircle.
Good. Remember that in any right triangle, you could put a semicircle around the right triangle. So, if I could put a semicircle from here all the way around to here, wherever the semicircle crosses this line, that's the top of the right triangle. That's the vertex of the right angle. But to do a semicircle, we need to know where to put the point of the compass, and that's going to be the midpoint. So we'll open the compass up more than halfway to that end over there. And right about there's probably fine. Make a nice big arc. Make an arc above. Make an arc below. And again, as I mentioned before when we were doing the mean proportional, don't necessarily want to draw the whole line super dark or anything. I really just need that little point right there, that midpoint. So that, as Quentin said, we can construct the semicircle. So put the point there on the midpoint you just found, open it up to the end, or to the other end, it's up to you. And put a semicircle around it. And if we wanted to before, I said you could actually draw the right triangle, if you were so inclined. I'm not really so inclined, but you could do that. Again, don't lose sight of what we're going for, though. I did need to find the mean proportional right here. This is S. But the objective was to find S so that class I could construct a square. Well, remember, to have a square, you need a right angle. I have one. And you need all the sides to be equal. Equal sides means endpoints could be made to coincide, meaning if I measure the distance between the endpoints right there, that's the length of my side. So right here, that's the length of my side. Right here somewhere, that's the length of my side. If I go up here, right here somewhere, that's the length of my side. And so right there is that top corner. So if I simply connect the dots, I will have my square. And the area contained in here is exactly equal to the area contained in here. We have transformed the triangle into the square. How many pretty much nailed it for homework last night? All right, for those who had some struggles, does it make more sense now? Do we remember it now? Still makes no sense. Well, let's practice a similar version of this, if you would. I'm going to take out another sheet of paper, and this time we're going to start not with a triangle. This construction has possibilities beyond its own self. And while we memorize, perhaps, the steps to construct a square equal to a given triangle, we could go further and apply the idea of the construction, that is, starting by setting area formulas equal to each other. We could do that with really any figure. So let's take something like, for instance, I don't know, a parallelogram. Let's draw a parallelogram on our paper. So just start by drawing any length line. And then draw some slanty line. Now, of course, we do want our parallelogram to be perfect, don't we? So we're not going to draw any more lines, just those two. And then you'll measure that first line you drew. Go to the top of your slanty line, make an arc. Then measure the slanty line, go to the other end of the base, and make an arc. And when you connect the dots, you'll have a perfect parallelogram. How do we know? Because opposite sides have to be equal. That's what, you know. You don't want to spend a long time trying to freehand it and make it look all nice that way when this is really pretty quick and easy. So there's my parallelogram. And I want to turn my parallelogram into a square. I want to turn my parallelogram into a square. Again, as seems to be the case always with this stuff, since transforming means to take the area of one and make it equal to the area of the other, we should start with our area formulas. What is the area of a parallelogram, Chris?
PA equals BH. PL equals BH.
So in other words, instead of PL, I can say BH. And for the area of a square, Genesis, so I can say that BH equals S squared. And following the pattern of what we did in construction 21, again, this is technically not construction 21, but it follows the pattern, we can make a proportion, Jamie.
B is to S as S is to H.
Did you hear how she did that, Ethan? I'm just picking on you, man. All right, and so guess what we need to construct, class?
Square.
A square, mean proportional. I know B, I don't know H. Thoughts?
We don't need to know it. Oh, you do need to know it.
I do need to know it.
Draw an altitude.
Draw an altitude. And really, remember, the altitude could go anywhere in here, right? So, I don't know, pick a random point. Now, we could pick a point at the top, or we could do the whole umbrella construction. There we go. It's not a smiley face right now. If you pick a lower point, right, you would have an umbrella construction. And you, and then you could, there's a little storm cloud up above the umbrella. Maybe this is, this, with the lightning is going to come down. I don't know. Or you could do the little construction 4, where you make a little mark on either side of the point and open up wider and connect. A number of ways. In fact, technically, you could do a perpendicular bisector. I don't care. You just need any perpendicular that runs between these two lines. So there's my H, there's my B. Notice, I don't have to find half of B this time, right? On the triangle, you do. Parallelogram doesn't have a 1/2 in there, does it? I don't need to cut the base in half. I'm good. So I've got my base, and I've got my altitude. I'm ready to construct the mean proportional. What do I do first in constructing a mean question first?
Yeah. So, can you use the sides of the parallelogram as the sides of the square?
No, Chris. The sides
so
of the
disappointed in me.
well, the sides of the square are all equal. Are the sides of the parallelogram equal? No.
I meant like the.
So we're ready to construct a mean proportional so we can find how long the sides of the square are, right? That's our mission. And Chris is like, I've got to figure out how to find the sides of the square. And he tried to find a shortcut. It wasn't there. But the point was he needed to know the length of the side. Well, let's find the length of the side, or better yet, let's construct the length of the side class by constructing a mean proportional, starting with a, Ethan,
Big long line.
big long line. Something about Ethan, and I just always a big long line, big long line. Whoa. And then Kendall, like little short line, little short line. I'm just picking on you, Kendall.
Honey, I shrunk the kids.
She shrunk so small we can't see her anymore. I'm just picking on you, Kendall, because you're not in here right now. Well, actually, I would pick on you if you were in here right now. But anyway, so on the big long line, though, Ethan, what do we do?
Draw the base.
Measure the base.
Yeah, measure it and then draw it.
So you mark it off.
Mark it off. Thank you.
Yeah. The drawing's technically already done. It's just a matter of finding the measurement here. So
Exactly.
there we go. Yeah. All right. So there's the base, and then what?
Mark off the height.
Or the altitude, technically.
Measure it.
Measure the altitude. There we go.
Technically.
Technically. And then mark it off in succession, right, Ethan?
Exactly.
We don't use the street terms.
And scribble off the y-axis there. We don't care about that. All right, and we could label it too if we wanted to, right? Here's the base. Here's the altitude. So, all right, let's see here. Now what, Chris?
I'm gonna be 100% with you. This is where I went off track.
Well, we just did one of these, so if you're paying attention, we should remember.
I was.
Okay, maybe Quentin remembers.
No, I can do it.
No, Quentin, Quentin forgot last time, so I need Quentin to answer this one.
Bisector. No. No.
That's what you said last time, and it was wrong. And maybe if I try again, he'll say it's right. Definition of insanity, doing the same thing over and over again, expecting a different result. All right, Chris has it.
Perpendicular.
Perpendicular, we're good. Right here where B ends and H begins, right in between them. I'm gonna put a little perpendicular right there. So, little marks, open the compass wider, arcs above, connect los dados. That's Spanish for the dots.
Is it actually?
No.
What kind of Spanish is that?
I didn't think so.
No, it's made up Spanish.
Do we know that Spanish?
I don't know. Doesn't sound like any Spanish you've learned, right?
Los estidos.
All right, and then what do we need to do, Quentin?
No.
We just did a perpendicular.
Bisector.
We need to bisect so we can find the
Midpoint.
midpoint so we can make a
Semicircle.
semicircle. There we go. Okay, so remember it's going to be the whole thing from the end of H all the way to the beginning of B. You're going to measure up half of that. Arc to the other end, arc above, arc below. And again, this is not this line means nothing to me. It's the place where it crosses. It's the midpoint is all I really care about with this line. So
You just open it more than half?
open more than half, make the big old arc above, arc below. Go to the other end, arc above, arc below. This is construction one, the first construction we did at the beginning of the year. And get that midpoint so that,
My lines don't intersect when I do that.
then open it wider.
Okay.
Open it wider still. Like there we go. And then go to the other end.
I already did that.
No, you changed. I think the compass was open though, so you have to do it again. There we go. So connect those two dots and find your midpoint. And then of course we can draw our semicircle. Looks like Ethan's already finished. Show off. And
Easy.
matter of opinion. Other people don't necessarily share that opinion.
I know.
But you're entitled to your opinion. And so, so we have right here to right here the length of a side of the square. And now normally, class, you'll notice that once we get that side, I measure it and I kind of go off to this side. But you notice I'm kind of running out of room. But I got plenty of room over here. It doesn't matter. All you need is a right angle. There's a right angle on both sides of that perpendicular, right? So it doesn't matter which side you go on, whichever side has room, because I'm lazy and don't want to do any more work than I absolutely have to. And there's 1, 2, 3, 4 vertices of the square. We'll connect the dots. And we will have a square that is exactly equal to the parallelogram we drew at the beginning. This area equal to that area. Questiones on el dado. I should probably stop.
Yes.
Questions on this? A YouTube channel gets flagged as offensive to Hispanics and Latinos.
Oh wow.
No offense. Hey, look, I think your language is cool. I just can't speak it. All right, I'm trying.
Language is cool.
E for effort.
Better than,
You're trying to-
it's better than English.
Right?
All right, questions.
Los estudiados.
All right, construction 22 in your notebooks now. Construction 22 in your notebooks. Construction 22 is to transform any given polygon into a triangle. Construction 22 is to transform a given polygon into a triangle.
So we're doing the opposite of what we just did.
We were transforming a triangle into a square. Now we're taking a random polygon, for which we probably don't know an area formula. We're going to turn it into a triangle. Transform a given polygon into a triangle. Now we're not going to use area formulas here, because the given polygon may be one we got an area formula for. For instance, once you've written this down, if you would, go ahead and draw a, I don't know, kind of a goofy looking quadrilateral of some kind. So just kind of a random, it's not anything. It's not a rhombus, it's not a trapezoid, it's not anything. It's just a quadrilateral. It's just a big nothing burger. Now let's call it ABCD. Now I'm going to explain the proof of this after I show you the steps. So we're going to actually do it, and then I'll explain why it works, as opposed to talking through the proof first. Step number one, bottom third of the page, is to draw diagonals from the top vertices to the base. Draw diagonals from the top vertex to the base. Not top vertices, top vertex. Well, correction, depending on the polygon, you may do top vertices.
Are we doing top vertices?
We're only doing top vertex. Yeah. Draw diagonals from the top vertices, or in this case, there's a top vertex, to the base. So my top vertex could technically be C or D, right? Either one of them. D is a little bit higher, so I'm going to go with D. And the only diagonal you have is from D to B. So that's step number one, draw the diagonal. Or if there were more diagonals you could draw, you would do that. Well, I don't have more diagonals, so that's it. Step number two is to construct parallels, or in this case there's only one parallel, but construct parallels through the side vertices. Construct parallels through the side vertices. And in parentheses, it's kind of construction 10, but I'm going to use alternate interior angles here. So using alternate interior angles. Construct parallels through the side vertices. Now here's the idea. C is a side vertex. I could make a parallel right here, correct?
Correct.
Somewhere right there. This angle 1 and this angle 2, if they are equal, I will have a parallel, correct? So what I'm going to do, watch closely and then kind of do this with me, is I'm going to put my compass down here at B, open the compass up enough. I mean, this is pretty slim right here. So if I don't open it very much, I've got a really tiny arc to try to measure. I don't want a tiny arc. I may even open it up almost to the vertex and make an arc. That's my angle 2. But then I'm going to reverse the compass, and up here at C, out here on the side, I'm going to make another arc. And when I measure, that's going to give me my parallel. Okay, so at B, arc, flip the compass at C and arc down here, so that when I measure across the known angle 2, I can then come down here outside the polygon and make a parallel. I'm going to come around and make sure we all understood what I was talking about there. Other than you, Kendall, I'm not going to check your work. Because I know you're smart and you definitely got it. Ethan's real closely. Okay, so this is an angle right here. The alternate interior angle would be out here somewhere. So what you want to do is your compass is really loose. All right, so yeah, let me tighten that for you. That's going to do nothing. You know what, actually, I'll fix it after class. Let me give you a different one to use right now. Just use this one. Much quicker. All right, and then but you measure here, and then you measure out here to get alternate interior angles. That looks good. That looks good.
Thank you.
Hey, there you really got a side vertex sticking out there. Good. That was really far out. And all right, but that it's correct. All right, and then when we connect C through the point, we'll have a line that runs parallel to the diagonal. All right. When you draw your diagonal, by the way, if you haven't already, make sure it's long enough that it would come down below, slightly below this base level, because step number 3 is going to be to extend the base to meet the parallels. Extend the base to meet the parallels. Again, in this case, we only have one. And I'm going to call this point here E. Call this point E. Step number 4 is to connect the parallel base intersections. So it's like hyphenated, right? It's a hyphenated name. Connect the parallel hyphen base intersections to the top vertex. Connect the parallel hyphen base intersections to the top vertex. So from E to D, we'll connect the dots. And now you have a triangle, A, E, D, that's exactly equal in area to the original polygon. Why? That's the hard part. This one's a little bit confusing, so I want to talk through the proof very quickly with you. If we were to call this point P, but before I do, we all connected D to E, right? Easy step? Okay, good. Consider this for just a minute. I want you to look at this triangle, DCE. Do you see it right here on the outside? DCE. If we had thought about it from this perspective, that CE is the base, then the altitude to the base would be the perpendicular somewhere out here, correct? This perpendicular is the altitude of this obtuse triangle if this is the base right here. I also want you to look at BCE. You see BCE? Again, if we look at it from this perspective so that this is the base, then the altitude's right here. Well, what's true of this altitude and that altitude, since these lines are parallel? They're equal, because they're parallel lines included between parallel lines. So these altitudes are equal, and they're both the same base, right? Triangles having equal bases and equal altitudes are equal. So what that means, class, is that BCE right here and DCE right here have equal areas. Now you notice BCE includes this little outside sliver, right? As does DCE. It also includes that little outside sliver. So that area is equal to itself. So that equal area could be subtracted away from these equal areas, meaning that this region here is left over from DCE, and this region here is left over from BCE, which means they're equal. Because you subtract equals from equals, they're equal. So all I did was transform DCP's area, and I put it inside BPE instead to form a triangle. So that's the proof behind why this construction works. I want to do it one last time, but I want to do it with a pentagon this time. So flip the page over, and we'll do it with a pentagon instead of a quadrilateral. Actually, I think it's a little easier with a pentagon, to be honest with you. All right, so start by drawing some sort of pentagon. 5 sides. That'd be octagon, Ethan. I know you were kidding.
Was it?
I really
Make stupid comment, get stupid response.
For a second I was drawing a stop sign, so I don't know what I was saying.
That's octagon. Yeah, that's 8 sides.
Look, great minds think alike.
instead of theirs. All right, so let's call this A, B, C,
I'm calling administration.
D, E.
Wait, he is administration.
All right, so we've got our pentagon here, and we want to turn this pentagon into a triangle. Flipping back to the previous slide. Step number 1, class. Diagonals from the top. From the top, we're going to draw the diagonals down to the base. That's going to go D to A, D to B. D down to A, B down to B. Step number 2.
Construct parallel lines through side vertices.
Notice that C and E are your side vertices. They're jutting out on the sides. We want to put parallels. Now, DB is going to get a parallel through C. DA is going to get a parallel through E. So I've got angle 1 and angle 2 are going to need to be copied out here at 3 and 4. Make sense? Now, I will say, if your pentagon is really small, you're going to have a really hard time doing this. So bigger is better. It makes it easier if you have a nice big polygon to begin with. But remember, watching, and then you do, make an arc across angle 1, come up to E and make the arc outside the polygon. Do the same thing with 2 and 4.
Is it okay if the line that we draw outside the circle doesn't touch, like, say, side A?
Let me see what you're talking about.
So, like, I didn't extend it all the way up here because I didn't feel like I needed to.
Alright, so this is your base.
Yeah, right over here, I'm saying, like, over at A, I didn't extend all the way to the vertices, so it's obviously not going to touch there. That's fine, though.
What do you mean it's not going to touch there? Okay, so you make an arc. You come up here. You make an arc.
Okay, I didn't know if it was okay that it didn't go through there.
No, mine doesn't either at A. My B it almost does, but at A it certainly doesn't. And it's almost, I was like, I don't really want it to go all the way to the other end necessarily, but I was too lazy to change the compass.
Fair enough.
Now it's beginning to look somewhat like a tent. Alright, how many have both parallels drawn? Okay, several of you. Alright, what do we do once all the or I say all, there's 2 of them. What do I do once the 2 parallels are drawn, class? Extend the base out to meet it. Now, I will throw this thought out there. You could have, I suppose, when you were first drawing the pentagon, you could have just started off with a big extended base, I suppose. Or if you were given a pentagon on a piece of paper for a construction quiz or on a test or something, you could always start by extending the base up front, but I don't know if this saves time considering you have to do it at some point anyway. All right, and I'm going to call these points M and N. M and N. All right. Now what?
Send them up to the top vertices.
Connect the M with D and N.
Good. Go D to M and D to N.
Never done right.
And we're done. We've got a triangle
Nice.
that is equal to the original pentagon.
It's easier than the last one.
Again, we've basically taken this piece of triangle here and we put it right down here. We took this little piece and we put it down here so that D MN is equal to the original pentagon.
I will say, without different colors, it's probably going to look like just a bunch of lines.
Yeah, I like to shade in the finished product so I can see it. That's only for my own sake, or Genesis uses a highlighter, that's fine as well. But yeah, I mean, shading to me is helpful. since I usually just use pencil when I'm doing it on my own, just so I can see where the triangle's at. Because you're right, there's a ton of lines here. Now, we're not going to do construction 23 for sake of time, but I want to talk to you about construction 23. Construction 23 is to transform any polygon into a square. And it's basically, you do this, transform it into a triangle, and then take the triangle and transform that into a square. So you would construct the altitude. You would bisect the base and find the midpoint. You'd measure half the base and the altitude off. You'd construct the perpendicular. You'd find the midpoint, do the semicircle, you'd make a square. It's basically construction 22 and 21 put together. Okay? We're just not going to have time to get that far. So we're going to leave them as separate constructions.
It's just tedious, it sounds like.
There's another thing I'd like to show you since I have time. Well, this is our last day of new material. Monday we have to start review. Is a hexagon. Because a hexagon is a little bit unusual in that there are two clear top vertices. And there would be, you can only draw to the base. So with a are you watching? With a hexagon, you would actually draw one, two diagonals, but from separate vertices. You would then construct the parallel, and the parallel, extend the base, but when you connect the dots, notice you don't have a triangle. What do you have, class? Or at least a quadrilateral, right? It kind of looks like a trapezoid. So then how do you make that a triangle? Well, you now say these are now my 4 points, and you go back to what we did on the front side of that page. You draw one diagonal, you construct a parallel, you connect it out, and then you connect it over, and there's your triangle. So you basically have to do the construction 2 times. So you go beyond 5 sides, 4 sides, 5 sides, you have a clear top vertex. Once you get to 6 or 7 sides, you're going to have to do the whole thing twice. You go to more sides, you do it more times. But still the point is, it works for any number of sides if you're willing to stick with it long enough. Since I have mercy on your souls, we just did 4 and 5. But I wanted to show you that it could work for more and how it would work for more. Questions on those other kind of advanced concepts? Yes,
So
sir?
you can literally use a duodecagon and do it.
You could. It would take a long time to do.
Like 30 minutes.
And good luck keeping up with all the lines. But I mean, you could in theory. So if you were really bored in study hall one day, draw yourself a duodecagon and turn it into a triangle. Or better yet, why stop at triangle when you could turn that into a square?
I'd rather copy
I don't think
that.
I would ever be that.
I'd rather go.
No one's ever that bored. All right.
I'd rather jump off the hill.
All right, I'm not giving you any written homework this evening. However, I do need you to make sure your notebooks are ready to go. Just remember, this is going to be 2 quiz grades. They're at the end of the quarter, so it can really boost your grade and help you out a lot, especially if you're right there on the edge of an important line or something. Or it could, stay put, hurt your grade if you don't do a good job with it. You'll turn your notebook in on Thursday when you take your exam. That's in lesson 173. So Thursday's the exam. That's when notebooks are due. Except to you, I need your notebook Monday. So you got, depending on how much work you have to do over the weekend. But your notebook I need Monday. The rest of you notebooks due Thursday when we take the exam. All right, have a wonderful day. You are dismissed.
Are you leaving?